Hey, everybody. Welcome to the Chapter 9 guided assignment. Um, I guess that's the only preamble I have is welcome. We're going to be covering hypothesis testing in this chapter. And so the guided assignment will walk us through a few examples. And so the first one is just going to show us how to go about, I guess, thinking about a hypothesis test and how we set up a hypothesis test. So let's just start with it. The manager of the Danvers Hilton Resort stated that the mean guest bill for a weekend is $600 or less. A member of the hotel's accounting staff noticed the total charges for the guest bill have been increasing in recent months. The accountant will use a sample of future weekend guest bills to test the manager's claim. So which form of hypothesis should be used to test the manager's claim? So typically, we call the claim, or if it's not a claim, it's just what we think things have been, the normal that the status quo, things as they are. We call that the null hypothesis, and we list it with a H sub 0. So our null hypothesis is that the mean is less than or equal to 600. And then our alternative hypothesis, sometimes people call that a research hypothesis. What we're going to be testing for, our alternative hypothesis is that it is greater than 600. So what we're saying is currently we think that it is less than or equal to 600, but we have some evidence that indicates it may have gone up. So we're going to test to see if it's greater than 600. So the null H sub 0 means the current status of things or the status quo. And the alternative is the thing that we're going to see if we can test or check to see if it really has gone to that. Okay. So when the null hypothesis H sub 0 cannot be rejected, can we conclude the manager's claim is wrong? And the answer is no. So if we can't reject the whole null hypothesis, then that means we still think that it is less than or equal to 600, which is the manager's claim. And when the null the null hypothesis can be rejected, can we conclude the manager's claim is wrong? And the answer is yes. At that point, we believe that it is greater than 600, which means we would reject the null hypothesis and accept the alternative hypothesis. There's the first one. And again, that's just meant to give us a feel for how hypothesis testing works and how these problems are made up. So next, we have a situation where it actually wants us to consider a specific hypothesis test. So it's already given us the hypotheses, and now we're supposed to work it out. So the way these are set up, and the way they, not just set up, but the way they are, okay, is we have some hypothesis tests where we are testing to find the population mean, meaning our hypothesis relates to the population mean. So we'll see right here, that means the population mean is greater than or equal to 20. That's our null hypothesis. And then here, the alternative hypothesis is that the population mean is less than 20. So anytime we are testing to see if something is, to see if the population mean has gone down, okay, that it is less than something, we're going to call this a one-tailed test, meaning we're only looking at the one side of the normal curve. And then because we're testing to see that it is less than, we'll be looking at the left hand or the lower side. So this is called a left-tailed test. Sometimes we'll see it where it's the other way, where our alternative hypothesis is that it is greater than 20. Then we would call that a one-tailed test, and it would be a right-tailed test. And then sometimes we're looking to see if it equals or doesn't equal something, and that would be, so anytime the null hypothesis is that the mean doesn't equal a number, then we'd have a two-tailed test. And we'll have an example of those so you can see them in a minute. So we have to know if the population mean, we have to know if we're dealing with population mean or population proportion. So this is a population mean. And then we have to know whether or not we know sigma. And if you remember from earlier, sigma means our population standard deviation. So we have to know, because if we don't have the population standard deviation, we'll have to use the sample standard deviation and then use a t-distribution instead of a normal distribution. All right, that's a lot of talk. Let's just get to working it out. So this tells us we have a sample of 50, provides a sample mean of 19.4 and a population standard deviation of 2.0. So still, for me, the easiest thing to do is just to write down what I know first. So n, or sample size, is 50. Sample mean, sometimes that's called x bar, that is 19.4. The population standard deviation, sometimes it's called sigma, right? That is 2.0. And then we also know that our hypothesized mean, okay, which I call that the null, or the hypothesis, the null hypothesis mean, is 20. So I call it null. You can call it hypothesized mean. You can call it whatever you want, but it's this number that we're testing for, okay, which is 20. So this is the information that we have available to us right now. So we want to create a test statistic. And there's really no other way to do this other than by using a formula. Okay, in other words, there's not an Excel function for this. So the formula, I'm actually just going to bring the book over here for a second and show you it. It's in the book, but the formula is right here, which is x bar, our sample mean, minus our null, or minus the mean that we are testing for, divided by sigma, which is the population of the standard, the standard deviation of the population, divided by the square root of n. Okay, so I'll show you how to make that function in Excel. They don't have a function for it, but we can create our own little formula here. We're going to say the numerator is x bar. Whoops, I didn't hit equals, sorry. X bar minus the null divided by sigma, which is the population standard deviation, over the square root of n. And that gives us our test statistic. So in this case, we have a test statistic of a negative 2.12. Test statistic is always given to us in a z-score. So what that's saying is, given an n of 50 and a sample mean of 19.4, and that we're testing for a hypothesized mean of 20 and a population standard deviation of 2, that this sample mean would be 2.12 z's below the mean. So we know our sample is less, but is it enough less that we can, that we can believe that the population mean has truly gone down, right? Because the population, or the sample mean, could be a little bit less than the population mean, but because of standard deviation, it doesn't necessarily mean the population mean has actually gone down. So that's what we're trying to figure out. So the next thing we'll figure out is what's called the p-value. Really, that just means what's the probability of getting that test statistic. So we're going to do equals norm.s.dist of negative 2.12 of the test statistic, comma, true. So you'll remember this just returns to us the probability of getting a z-score of negative 2.12 or less. And that's pretty low. It's 0.01695. They want us to do it to 4 decimals, so we will 2.0169, or about 1.7%. All right, so using an alpha of 0.05, can it be concluded the population mean is less than 20? So what we're trying to figure out here is this test statistic that we calculated using the sample, is it enough less than the mean that we can conclude that the mean really has gone down? And so the way we use the p-value approach is we say, if the p-value we calculated for this test statistic is less than the p-value of alpha, then we're going to conclude that the mean really has gone lower, meaning it is lower enough of the mean, or than the mean, then that we think that probably is highly likely that the mean really has changed. Okay, so we're going to say, yes, given this, we can conclude the population mean is less than 20. Then it says, what is the rejection rule using a critical value? Use an alpha of 0.05 and round your answer to 3 decimal places. So The other thing we can do is we can calculate what's called a critical z, which in essence is just the z-score of the alpha, okay? So the z-score of the alpha in this case, we're just going to do norm.s.inv, and we're going to put in the alpha of 0.05. And so we see that the z-score of the alpha, rounded to 3 decimals, is 0.16 or negative 1.645. In other words, we're going to reject the null hypothesis if z is less than negative 1.645. So now we're looking at it from two ways. One way is the p-value, which says if the probability of getting the test statistic is less than alpha, then we'll reject the null and accept the alternative. The other is if our test statistic is less than our critical value, which is the z-score of the alpha, then we're going to reject the null and accept the alternative. So using the critical value approach, can it be concluded that the population mean is less than 20? And the answer is yes. So no matter which one we use, we're going to come to the same conclusion. That is, since we're looking at the left-hand side of a normal curve, I don't know if it'll help, but let me show you a normal curve here. So we're looking at this left-hand side of the normal curve. The mean is always at the high point of the normal curve. So when we're saying, hey, I think that the population mean is less than 20, and I did this test, and in the test, I found a sample mean of 19.4 with a standard deviation of 2.0. Is that 19.4 enough less than 20, 19.4 on the sample, enough less than 20 that I can conclude that the population mean really did shift to the left or become smaller? And what this tells us is there's a higher probability of the alpha than there is of that p-value being found. So yeah, it really does look like it shifted to the left, okay? So I hope that helps a little. It's a little confusing until you get used to it. So I'll check my work and make sure it's right. Uh-oh, looks like I messed up. Let's see, compute the value of the test. Oh, I just wanted 2 decimals. I was like, wait a minute. So this says that, and we're going to reject the null hypothesis if z is less than or equal to. Sorry, that's my bad. Let's see if that works for us. Okay, so there's problem number 2. So problem number 3 is going to be similar, where we know the sigma, but in this case, it's an equal to or not equal to. So what we're saying now is we can reject the null hypothesis if our test statistic is either too small, meaning too far to the left of the mean, or too great, too far to the right of the mean, okay? So we've got a couple things a little bit different. So again, let's start with what we know, and then we can calculate the other stuff. So we know the sample is 75. We know the population standard deviation is 10. Looks like they're going to give us different X bars for each problem. So we'll get to that in a minute. The null, or the hypothesized mean, is 22. And then we'll have to calculate the test statistic, okay? So I'm going to start with this first one where our X bar is 23. So remember, the formula for our test statistic is X bar minus the test, or minus the null, okay, divided by the population standard deviation over the square root of n. So again, I'll punch this in here. So we're going to say X bar minus the null divided by population standard deviation divided by the square root of n. So in this case, we get a test statistic of 0.87. That means that this X bar, this sample mean, 23, is 0.87 standard deviations above the mean, okay? So now we have a couple of issues. The first is if we find the p-value, well, the p-value, the probability of getting this has to be two-tailed, okay? So what that means is when I do equals norm dot, whoops, dot s dot dist, and I put this z-score, true, this is going to give me this big giant p-value of 0.8067. What we have to realize is when we're doing a two-tailed test, in essence, we're finding 2 points, okay? So let me see if I can bring you up a picture that might help, because I think this can be a little confusing too. So now we're saying, okay, so we need the probability of not only a test statistic of 0.87, but it's actually the probability of getting less than negative 0.87 and more than positive 0.87. So these two regions here are the regions in which we would reject the null hypothesis. Because on a two-tailed test, we're not just saying, did it get smaller or did it get larger? We're saying, did it either get smaller or larger? Did it get far enough away from the mean in either direction that we have an issue? So what we're going to do is we're going to so here's our test statistic of 0.87, okay? So we have to figure out the p-value of a negative 0.87, which we can do just by doing, let's see, that. So that tells us we have a p-value of 0.1932, which would be from 0.87 and down. And then we also need the p-value of positive, which is going to be the same, right? This is a little confusing at first, but the idea is because this is symmetrical, the probability of plus or minus 0.87, a test statistic of 0.87, is going to give us this region, which has a p-value of 0.1932, plus this region, which has a p-value of 0.1932. So our total p-value then is going to be that times 2. So there's the probability of finding this. So I think for our z-value, it wants us to put 0.87, although really in theory, it should be plus or minus that. But we're going to use this. And then our p-value, it wants to 4 decimals. So 0.3865. And then we're going to compare that to our alpha. Our alpha is 0.01. So if our p-value is higher than our alpha, we will choose not to reject the null hypothesis, meaning it's more probable that we got this result of an x bar of 23 than the alpha. All right, so I know this is a little confusing, but remember the reason we have to do this times 2 thing is because our rejection range includes 2 tails, one on each side of the distribution. So what we're doing is we're finding the probability of this lower amount times or plus the probability of this higher amount, but we just find the probability of this lower amount times 2, okay? So on the second one, we have an x bar of 25.1. Now that we have our calculator created, all we have to do is put that in. We don't need critical z, that was from the last problem. So now we can see that with 25, our test stat goes up to 2.68. And so our p-value is 0.0036 on each tail. So that times 2 is 0.0073. And in this case, this does not exceed our alpha of 0.01. So we're going to say we're going to reject the null hypothesis because it really does look like our population mean has increased, in this case, increased more, further away from the mean. Just remember that with two-tailed tests, we can reject it on either end of it. So if it had gotten too small or too large, we could still reject it. So the last one is an X bar of 20. So this is going to return to us a negative test statistic, okay, or a negative z-value on our test statistic. So that's going to be negative 1.73. Where this gives us problems with our calculator is now our p-value was set to give us the negative of, or the probability of negative test statistic. But in this case, we don't want it to be the negative. We just want it to be the z-score. So we're always looking for that probability on the outside of these lines. So when so on a one-tailed test that's positive, right? If we use norm.s.dist, it's going to return this whole amount. But what we want is this amount, the probability here. When it's a negative, we just want, it'll return this amount, which is the amount we want, okay? So that can be a little confusing until you get used to it. So in our case, we want to know this plus this. So we're saying our test statistic is plus or minus a z of 1.73. And so we're going to use norm.s.dist of negative 1.73 to give us the p-value of this section. And then we're going to go times 2 so that it will be this section plus this section, 0.0833. Looks like I forgot to put in my test stat of negative 1.73. And so our conclusion here, our p-value is negative 0.0833. Our alpha is 0.01. So since that is higher than our alpha, we're going to say do not reject the null hypothesis. And there we go. All right. Hopefully you can work through that. It is a little confusing, I know, but once you get used to it, it's not too bad. All right. So we get on to number 4. And here you can see that it's the same type of thing, except now we have a right-tailed test because our alternate hypothesis is that the population standard deviation, or population mean, sorry, is greater than 12. But we don't have a population standard deviation. Instead, we have a sample standard deviation. So this is where sigma is unknown. The good news is it's almost the exact same setup, except instead of population standard deviation, we'll use sample standard deviation in its place. So again, I'll start with what I know. I have n of 25. X bar is 14. It's the sample mean. The testing or null mean is 12. The sample standard deviation is 4.32. And now I'm ready to calculate my test statistic. Okay, so the formula for the test statistic is pretty much identical to the one for the other one-tailed test, except instead of sigma, the population standard deviation, we'll use S, which is the sample standard deviation. In every other way, it is identical. And so let's see. I'm scrolling through the book right here just to show you. I guess I don't have it written down. Okay, so it's the same exact thing. So to find the test statistic, we're going to say this equals X bar minus the null, or the hypothesized mean there. And then we're going to divide that by, instead of sigma, S, the standard deviation, divided by the square root of n. So there's our test statistic, 2.31. Check our work. Looks like we're on the right track. This tells us to use the t-distribution table, table 2 in the appendix B, to compute the range for the p-value. You can use the table if you want, but I just use t.dist. Oops. And what's cool about the t-distribution is it gives you a 2t for a two-tailed or a RT for a right-tailed. So I'm going to use RT because this is a right-tailed test because we're testing that the alternative hypothesis has gotten bigger, okay? And then I'll use X, which for X, I'll use my test statistic. And then for degrees of freedom, we'll use N minus 1. And so that'll give us our p-value of 0.0147. This wants a range, so I just find the range that includes that. So 0.0147 falls between 0.01 and 0.025. So with an alpha of 0.05, what is our conclusion? Well, an alpha of 0.05 is greater than our p-value of 0.1047, so we're going to not reject the null hypothesis. Wait a minute, no, our p-value is less than. So sorry, we will reject the null hypothesis. See, it's confusing. Then it asks, what's the rejection rule using the critical value and use an alpha of 0.05. So critical value, sometimes I just call it crit value. And here we're going to do norm.s to inv. And then we're going to put in the alpha. Here's the problem though. If we put in the alpha, actually it might work just fine. Yeah, it's going to return us a negative critical value. So we can either put in 0.95, which is the what's it called? The opposite, not the opposite, but 1 minus the, I just drew a blank on the word. Or we can just do the absolute value of this to get the positive side. Complement, that's the word I was looking for. So our critical value is 1.645. So we will reject the null hypothesis if t is greater than or equal to the critical value of 1.645. And in this case, our test statistic is 2.31, which means we can conclude that we want to reject the null hypothesis and assume this proves or indicates in favor of our alternative hypothesis, which is that the sample mean, or the population mean, I'm sorry, is now greater than 12. Oh. Didn't like my critical value for some reason. Let me see. Oh, you know why? Because I use norm.s.inverse, but because we don't know sigma, we have to do t.inv, and then we also need to include the degrees of freedom, which is n minus 1. So there our critical value is 1.711. So yeah, we don't use normal, we use t when we don't know sigma. All right. So finally, we're on to the last one. I know, this seems like it takes forever, doesn't it? So here, we're dealing with the population proportion, and we're asking ourselves, has the proportion actually changed? So we can see our null hypothesis is that the proportion is greater than or equal to 0.75. And our alternative hypothesis is that it is less than 0.75. So again, we know we have a left-tailed test where we're checking to see if this proportion has gone down or gone to the left. So we'll start with what we know. N, our sample size is 300. We know the alpha is 0.05. And then our P bar, which is our sample proportion, it looks like it's going to change each time. So for this one, it's 0.68. Oh, and our hypothesized proportion, or our null proportion, is 0.75. All right, so I think that's all the info it gives us. So we need now the formula to find our test statistic. So our test statistic, let's see. I'm going to bring the book over. So it's just taking me a second. I just think it's easier if you can see it for a second. So the test statistic for hypothesis test is P bar, which is our sample proportion, minus the null proportion, or the hypothesized proportion, 0.75, divided by the square root of the null times 1 minus the null over n. Okay, so this should look a little bit familiar from stuff we've done before. So we'll go ahead and put it in here to find our test statistics. So the numerator is our P bar. Whoops, you got to start with an equal sign though. P bar minus the null. And then we divide that by the square root of the null times 1 minus the null. There's the numerator on the bottom over n. So our test statistic, and what's nice is it's returning this to us in z's, okay, is a z of negative 2.8. And then we can find the p-value just by taking the norm.s.dist of that z-score and saying true. And since we're using a negative z-score, we don't have to adjust that in any way. We just know that the probability of getting a z of negative 2.8 is 0.0026. And it wants these in 4 decimals, so that's just right. So in this case, our p-value is lower than our alpha of 0.05. And so that means we are going to so we're going to reject the null hypothesis. In other words, we're saying getting a sample proportion of 68.68 is enough lower than 0.75 that we believe the population proportion really has gotten smaller. Here we have a p-value of 0.72, or a p-bar. So now that we have our calculator made, we can just plug it in. Here we see our p-value is 0.1151. So in that case, since that is not smaller than our alpha, we're going to say, do not reject it. So getting a p-bar of 0.72 says, even though that is less than our sample, or than our hypothesized proportion, it's not enough less that we can conclude whether or not the population proportion has truly changed. For C, we have a p-bar of 0.7, which gives us a p-value of 0.0228. Again, that is less than 0.05, so we're going to say it is less than or equal, so we're going to reject. And then on the last one, we have a p-bar of 0.77. All right, so here we have our problem again, right? So now that gives us a positive test statistic. And so this p-value is going to be confusing because this is saying the probability of every amount to the left of 0.8. And what we need is we need to know the probability of the rejection range, right? Which actually in this case isn't true because this is a one-tailed test. So I think they're still going to want, let's see, 0.7881. We're going to say greater than, do not reject. Yeah, so that's going to work always with a left-tailed test. Even when we get a positive test statistic, it just means we're really not going to reject, right? Like, because it's actually higher. Our sample proportion is actually higher than our hypothesized proportion, which definitely means it has not gotten less. All right, so I hope this helped. I know it's a lot to sort of take in at first, but it's really useful in real life. So it's one that's worth kind of figuring out how to create a hypothesis and then test it. I hope you have a great day, and I hope this is helpful to you.